Today's video is the third and final part of the series on chiller minimum evaporator control. In the first two videos, we looked at getting the control strategy the right way around and incorrectly selected pressure transmitters. In today's video, we're going to try and mop up a few other things that you should consider if you're having problems with chillers tripping. So we're going to talk through incorrect PID loop settings, the chiller's startup and stage up sequence, where we have low flow problems quite often. We'll talk about mechanical value engineering, which causes big issues for us. And then finally, we'll just touch on do not use butterfly valves for bypass control, which I just had it last week again. So PID loop settings. So often I will find that we are doing witnessing and I'm asking the BMS guy, close 3 valves, close 2 valves, close 2 valves, close 2 valves. And as I'm doing that, I'm watching the flow, the chiller drop. I'm doing that during our witnessing phase to prove that when we get towards the 25 kPa chiller minimum flow setting, the bypass opens up and it sort of modulates. And as I'm closing more AHUs off, it's opening more, and that's how I do the testing. So usually, if I do this, I can get the chiller to trip, which I'm just basically simulating a low load condition. And one of the things that's often wrong is the PID loop settings. And how I notice that always is as I'm watching the flow, the pressure drop below the set point, so that set point is 25, goes 24, 23, 22, 21, chiller trips. And on the graphic, I look at the bypass valve position, and the BMS is only asking the bypass valve to be open, 25%, 30%, 40%. In other words, the flow dropped far enough for the chiller to trip, but we weren't trying very hard to keep the bypass valve open. And that's usually the proportional band is too wide. I think what happens is the software programmers in the office, they copy and paste a PID loop from somewhere else and they plonk it on there. They connect, the pressure sensor and the bypass valve and the set point. They do all that, and they just left some default proportional, PR settings. So let's say they've got 10. The proportional band's 10. So in this case, it would be 10 kPa, not 10 degrees Celsius, but 10 kPa. And a 10 kPa proportional band means that, and just forget about integral for a second, it means that if the set point's 25 kPa, it has to drop to 10 lower, to 15, and then the valve be fully open. So a 10 kPa proportional band means that you've got to be 10 kPa below set point before the valve is fully open. That's not good enough because we would have tripped by then. We need that bypass valve to be fully open, 2 kPa below or 4 kPa below. So whenever I'm watching the graphics and I'm forcing the 2 ports closed, I see the pressure dropping. I keep an eye on the pressure, and as soon as it trips, I look at the bypass valve. If it's not 100%, it means we're not trying hard enough. And people always say to me, and I'll defect that on the defects list, and the BMS guy will say, well, that's fine, we'll just do a bit of tuning. And that's very annoying for me because there is no time for tuning during construction. The commissioning techs are flat out trying to just get the inputs and outputs sort of working and going the right way. So if a commissioning tech is commissioning this control loop, does the program, he drives the bypass valve open, closed, make sure it drives the right way. You make sure the pressure transmitter is reading properly. You might get the mechanical guy to go there with their gauge, stick it on there and do a quick calibration. Yep, it's reading correctly. But the commissioning guy doesn't sit there for half an hour doing the process that I'm doing at witnessing, adjusting the valve positions on the AHUs and, simulating low load. There's no time for that. So just get the right value in the PID loop, in the software, in the office, 6 months before. Just plonk a thing there, think about it. What is the process variable? How's it going to work? And just get something that's decent in there. And then when you get to witnessing, because what happens usually is that at witnessing, when I'm sitting there looking at the BMS system, that's exactly the same time for the first time that the BMS guys saw the plant in auto. Before that was air and water balancing. So usually we're all discovering this for ourselves at the same time because there was no tuning happening. So get the right PID loop settings in there to start off with. The next thing is startup and stage up. When the chiller starts up, we've got our cooling coil. Those cooling valves are not going to be very open, probably. There'll be a max select cooling valve open to, say, 75%, but they're not mostly open, which means that when the chiller starts up, and the valves are mostly closed, and if the bypass is still closed, which it usually is, the chiller will be starved of water and it will struggle to get up and get going. So the default strategy here is that on the initiation of chiller system startup, we normally fully open the bypass valve before startup. So as the chiller starts up, as the pump comes on, that water has got somewhere to go because the two parts are mostly closed. So there's a lot of volume there for the water to run around the chiller circuit, the primary circuit, and the chiller will get away and get started up, and then the bypass valve will start to close after a time delay. That's the usual thing that we do. I stopped doing that about 3 or 4 years ago because I was finding out that on more critical applications like hospitals where we have theaters and things, and we have dehumidification control, and maybe in data centers, which is actually where I first saw this, opening these very big bypass valves, because they're usually oversized, it starves the field of water. So what I started doing recently is I was saying, on stage up from 1 chiller to 2 chillers, don't just override the bypass valve fully open, override the bypass set point from the minimum value to the design value. So when you're doing witnessing, I'm sitting there looking at the graphics, and we do a stage up and go from 1 chiller to 2 chillers. I actually want to see that the bypass set point got overridden from the 25 kPa to the 50 kPa. So by doing that, you just create this big gap between where we're controlling from and where the chiller cuts out, just for 3 or 4 minutes while the second chiller is getting going and it's sort of getting started up, and then you can release that afterwards. It just means that fully open in the bypass valve, we have truckloads of water coming through. The field is starved for cooling for a few minutes, and then we can start losing control, and then also other bad stuff starts to happen. So on system startup, fully open the bypass valve. On stage up, fully open the bypass valve. Alternatively, as an improved control strategy, on startup and stage up, override the bypass set point from its minimum position to its design position. So that will stop the chiller tripping when it stages up, because often on a stage up, that second pump comes on and it draws all the water, and it starves the running lead chiller of water, and it trips. So we often see the lead chiller trip on a stage up, and that bypass valve opening will help that. Now, value engineering. So a lot of you guys wouldn't see this because this happens before you're engaged, but the consultant will specify 2 high load chillers, 2 big chillers, and then 1 low load chiller. And they're doing that because they know that in low load conditions, as we've been discussing for the last 3 weeks, we can stage down to a small chiller that has a smaller pump and requires less flow, and it'll help us so much to keep that low load chiller running. It puts less pressure on us for bypass control. But the mechanical contractors will often value engineer out the low load chiller. And I think we might have touched on this on one of those risk mitigation videos actually. So they value out the chiller, and they know they're going to get rejected by the consultant, so they put a buffer tank in there, and they say, look, we'll use the buffer tank to discharge and to increase the loop volume. Now, quickly what that means is, when you have a buffer tank and you plonk it in there in the circuit, it holds a whole lot of water. So what happens is that the purpose is that when this high load chiller stages right off, the compressors turn off and it turns off the chiller, that tank is charged with cold water. And what happens then is, as we turn the lead chiller off and we keep the pump running, we draw off and discharge some of the coolant out of that buffer tank. So the buffer tank is almost like the low load chiller in that you can sort of draw off, it gives you some more time. Now the reason why we're doing that is because if you don't have that, the high load chiller stages off, on, off, on, off, on, like for 3 months during a shoulder season. It just cycles on and off because it comes on, it pulls the load down really quickly, down to 6 degrees, and it turns off, and then it gets depleted out. That 6 degrees water gets depleted out from the air handling units, and the chiller comes back on quickly. So the reason I put a buffer tank in there is so that when the chiller turns off, there's a longer delay before the chiller comes back on again, while it discharges the water, which means that we're reducing the cycle time, or we're increasing the cycle time. So the chiller can be off for a bit longer before it comes on. So it'll stage on off less than without the buffer tank. Why I'm mentioning this is, what I think we should do is, when we have this particular situation where we're very reliant on the buffer tank, we should, as we stage down from 2 chillers to one chiller and we stage down again, we should stage down to buffer tank mode or stage 0. In buffer tank mode, we turn the chiller off, we keep the pump running, and what we do is we measure the temperature coming in and out of the buffer tank. And what we can do is we can sort of detect that the buffer tank's discharging, and when the return water is getting warmer and warmer and warmer and warmer, it means the buffer tank's already discharged. Now, when the chiller comes on, we should turn the chiller on and we should adjust the chiller's supply water temperature set point from 6 to 10 or something. We're in low load, remember? So by doing that, the chiller comes on and it just takes up the load slower. The first compressor comes on, ramps up slowly, because it's not trying to get down to 6. So rather than the chiller coming on and just smashing the load in like 5 minutes, it comes on, it sees it's got a 10-degree set point, and it pulls the load down slower. And it pulls the load down and charges the buffer tank. And then turns off. So what I'm trying to say here is that we're sort of digressing slightly here, but we need to consider the buffer tank and adjust our control strategies. This is important to this discussion because if we just ignore the buffer tank normally and the chiller comes on, 6 degrees, smashes the load, chiller turns off. Chiller comes on, smashes the load, turns off. And that's bad for the chiller. Chiller will get buggered up. Like for a couple of years, that chiller will have problems. So in our minimum evaporator bypass control discussion here, you need to start thinking about the buffer tank when you have very more complex circuits. The last one is the easy one. Do not use a butterfly valve to control the chiller evaporator, because the butterfly valve is a quick opening valve. You want to have a globe valve or a characterized ball valve or something else that has an equal percentage characteristic. The butterfly valve does not work. It opens, the water gushes through, and then it does nothing for a long time here. And why I wanted to mention this was, because most people know that, but why I wanted to mention this was because we don't see butterfly valves creeping their way into air handling to control. Like, when did you ever see a butterfly valve and a fan coil in it? Like, never in your life. They seem to creep into chiller controls. And the reason why is because, in my opinion, the bypass pipe is a big pipe. It could be like 150 millimeters big or 200 millimeters big, which means that, a globe valve that big is extremely expensive. And then a linear actuator, well, it should be this way around. The linear actuators are very expensive. So people tend to not want to put globe valves in bypass control because the pipe is too big, it's too expensive. So they put a butterfly valve in there. They're cheap. And they have a rotary actuator, not the linear actuators. They're much cheaper as well. But it's not good enough. And actually, if you want to go really back to the original source of this problem, is that the bypass line is usually oversized because mechanical consultants and contractors will often size the bypass pipe to be the same size in diameter as the lead chiller. So the chiller's 150 millimeter pipe, the bypass is 150 millimeter pipe. That's not correct, actually, because remember, we have variable primary pumping. There's not a constant volume system like in the 90s. So the amount of water that goes to the bypass pipe is just the amount of water for the chiller and minimum flow, not the chiller in design flow. So the bypass line is always oversized and the bypass valve is always oversized, which is bad control anyway, and it's exaggerated when you put a butterfly valve on there instead of a globe valve. Went through that pretty quickly. All right, that's it. I hope you guys learned something. It's the end of the 3-video series. Hopefully we have no more chillers tripping on low load. Please like and subscribe, and I will see you guys in more than 1 week, because I've recorded a few of these videos today. Thank you.